Okay, so this video is going to be focused on free body diagrams, some of the rules of drawing them, and then there will be a bunch of examples that I go over that will hopefully be helpful in illuminating some of these sort of ideas and guiding principles for drawing free body diagrams. So first, the purpose of drawing these free body diagrams is really just showing the forces acting on an object. And in this unit, we've been sort of connecting that to the motion of different objects. And the reason I put this little piece in parentheses here, that we don't show what the forces are that an object is exerting, will become very apparent when we get to Newton's third law, and you all have started to see that in class when we've been talking about Newton's third law. But if we have like a person here, and we're told that they're pushing something to the right, we know that the force that is exerted on them would be a force backwards to the left. So we always want to make sure that we draw the forces that are acting on this object or on this person, not what they exert on something else. Again, I think this first idea is going to be like one of the main focuses of that Newton's third law video. So if you have more questions on like sort of how that shows up, then definitely check out the Newton's third law video. Now, the other thing that we've been going over in class is that we generally show objects as boxes. I'm not sure if that's just because the physicists who started coming up with these rules were not good artists. I know I am not a good artist, so you will always see me draw these things as just plain boxes. For some of you who are more artistic, I think there's nothing wrong with drawing a more accurate representation of an object or of a person here, but we just want to make sure that it's clear sort of like where the boundaries of this person or object is, so that we really clearly define the system where we have these forces acting. The other thing that you'll notice that I did here is that our force vectors are shown going from the object. So for something like the force of gravity, we know that gravity always sort of pulls us down towards the center of a planet or to any mass. It pulls us towards any mass. So on almost all of our free body diagrams, you'll see us draw this gravitational force like this, and we'll label it Fg, and we'll talk more about labeling forces later in this video. But you'll notice that we never draw our force of gravity like this, and I'm going to do this in red to show that this would be incorrect, because this, it looks like the force is almost like going into or entering this object, but we always, just the general convention is that we draw these forces coming from our object or our person of interest, not the other way around. We don't draw our forces going into them. So that's an important rule to keep in mind to make sure that you're communicating in a consistent way. And the other thing that we've definitely talked about in class is that the length of these force vectors that we show acting on this object communicates something about the strength of those forces. So if I drew a vector that was upwards, that looked like this, what I'm kind of telling you is, if I drew this carefully, that this upwards force that's acting on this object, whatever it is, would be weaker than this downwards force. And of course, then if I switch this up, if I drew this as much longer, and I'm running out of space up there, but if I drew this gravity arrow a little bit shorter, then it would be clear that this maybe force of gravity, or whatever this downwards force is in this case, nothing's labeled and we don't have any information about the situation, but this force would be weaker than this upwards force because it's drawn as a shorter vector, which means that it's a shorter or a weaker force. Now, the only other thing that I can think of that has come up in class definitely is that we could have multiple forces going in certain directions, so we could have literally as many forces as is necessary, as are appropriate for a situation, acting in a given direction, and we could have forces going in all directions, multiple forces. There's no rule against like having multiple forces in some direction, and there's definitely not a need always to have a force going in all four directions. So both of those things are possible and okay. It just depends on us figuring out sort of what's going on in that situation. So that being said, let's talk about the different kinds of forces that we've been using in class that we'll use as the basis of our work here as well. So the first force that we've gone over a lot, it was one of the bases of our first unit, is the force of gravity. And force of gravity, we know, is just an attractive force between two masses, and we pretty much always have it on our free body diagrams, pulling us down as long as we're on some planet, and usually most of our problems will be on the Earth. Our label for that is FG, which we've used a lot before. I just showed it a second ago also. Now the other focus of our first unit on field forces or non-contact forces was this electrostatic force, which you all know about, is an attractive or repulsive force between two charged objects. And the way that we labeled that in that first unit was FE, our E for electrostatic. Now, the rest of these forces would all be considered contact forces. So our first unit was all about the non-contact forces, gravity and electrostatic. These forces can be applied over huge distances. But all of these, from electrostatic on down, these are all of the contact forces that we've been using in class so far. So normal force, we usually label, and you can, if you didn't already know this, probably guess, that's an Fn that we usually use. And what the normal force is that's a force that's exerted from a stable surface directly outwards from that surface. So an example of that would be like if we have an object that is on the ground, then the ground exerts an upwards force on that object, and it's what keeps this object from falling through the ground or the table or whatever stable surface this is. But anytime you have reason to believe or that you can see in a situation an object is on some kind of stable surface, whether that's a chair, a table, bench, the ground, or anything like that, then there probably will be a normal force, and it's always directly out from that surface. Now, the other forces that we've been talking about or that you see here are maybe a little more straightforward. I think normal force might be one of the more complicated ones, and that's an applied force. That's what a person does. So if we have a person pushing an object in a certain direction, then the force that that person exerts on the object would be an applied force. And you might be wondering why all these letters, why not just use FA? And the reason for that is because our air resistance also has an A in it. So with these A forces, we have to be a little more specific, and the way that we can label that in here is with an F air. Some of these labels are not universal, but just based on the sort of toolbox that we'll be using in class at this point, I just wanted to differentiate between those two. So sometimes you'll see this air resistance just as a drag, so some people will label this FD, and this was just sort of my decision for us. Neither would be better or preferable, really. The other force that I skipped over for a second, friction, that occurs between two surfaces that are rubbing against each other. And it always acts opposite of the relative motion of two surfaces or two objects. So if we're pushing an object to the left along the ground, friction would act to the right. Or if we're pushing an object forward, friction would act to the left. So we have to know something about the motion or about the motion that this is preventing, because friction can not only sort of impede motion that is happening, it can also prevent motion from happening. And we'll talk more about that later in the class. Now, tension is a force that acts along the length of a rope, string, cord, anything that we're like pulling along an object. So this cannot, it's not just a force that can act up, down, left, right. It can act in any of those directions. It just depends on the physical situation to tell us sort of what direction this that tension force would be acting in. And we'll look at a couple examples of that today. And then spring force, which we don't use a lot until we start talking about springs really in depth, talking about elastic potential energy. But we could go over that here, and there will be an example of that in a second. That's labeled Fs, and that's the force that a spring exerts. The kind of weird thing about a spring is that depending on, and here will be my bad artwork for a second. So we have an object sort of attached to a spring, and we could have a wall here that the spring itself is attached to. And the kind of weird thing about spring force, and again, we'll talk more about this with Hooke's law later, is that springs can either pull or push depending on whether they're extended beyond their equilibrium length or whether they're compressed to less than their equilibrium length. So we know if we stretched this spring intuitively, the spring would pull back on our object, and if we compressed this spring, it would push and try to extend and get back to its equilibrium length. So that's the slightly weird thing about spring force. Now, with that in mind, with all of those forces labeled and with our general rules for free body diagrams, let's go over a couple examples. So for this first one, we have an object being pushed to the right along the ground. So let's draw our object, and it's a good idea to label these. Right now, all of the labels that I'm going to use are going to be kind of boring because all of these examples, I'm just sort of using a general object so that we can look at like some examples of these forces. The first thing I'm going to put on here, I'm assuming we are not in outer space really far from any planets. I'll assume that we're on the Earth unless we're told otherwise. I think that's a pretty fair assumption. And the main gravitational force is the one downwards from the Earth. We remember from our first unit that technically we could draw 1,000,000, in fact way more than 1,000,000, little gravitational forces in every direction because technically everything in the entire universe is exerting gravitational pulls on this object, and we could draw them all every time, except we would run out of time and we would never be able to do anything else. So the main gravitational force that we will always draw is just the one from the Earth. Now, if we have this object, I'm going to be careful to use a different color for the things that are not this free body diagram. So this black thing is the ground. And I'm breaking some rules here because you don't really need to draw this ground. Technically, the free body diagram is just going to be what I have in blue here. So the object, the box here with these force vectors coming off. I'm just going to draw some of these other things to maybe help clarify the situation. And excuse my bad art here, but here's our person pushing this object to the right. Yeah, this is a stick figure person pushing that object to the right. Now, we know that the person is probably on the left side pushing this object to the right, but it would be incorrect of me, I'll do this in red because this would be incorrect, to draw their force like this as a rightwards force going into this object. Because remember that we always draw our forces coming from our object. So if they're pushing this to the right, then I'm going to draw that force to the right from the right side of that object. And since that's the force that this person is exerting, that would be an applied force. Make that a little bit. There we go. Now, the other forces that we have here sort of depend on our knowledge of the physical situation and how this object is accelerating or maybe not accelerating. So one thing that we can say for sure is that this object is probably not falling right through the ground. And the reason that it's not falling through the ground is because there's this normal force, Fn, that's preventing gravity from just taking over and bringing this object down into the center of the Earth or through whatever ground this person and object are on. And if we want to show that these two forces are equal to each other, that they're balancing each other out, and that this object is not accelerating upwards or downwards, we can use little tick marks. And I know we've practiced this in class, but it might have been a while since I brought up the relationship between that and, like, in a geometry class, if we wanted to show that these two legs of a triangle were equal, we just use little tick marks also. I could have put 100 tick marks on both of these. It doesn't really matter how many I put, as long as these two forces, since they're equal, have the same number of tick marks. So it's not like having one tick mark would say that this is weaker than like a 2 tick mark force. It's just that we show these pairs of equal forces there. That's an aside. Now, again, a key sort of phrase that tells us that we probably have this normal force, anytime we see an object like on the ground, that probably tells us there's a normal force here. Now, if we were on perfect ice and the ground were perfectly slippery, this person might be in trouble a little bit. It would be hard to exert a force, but there would be no friction. But since we're not told that there is friction, let's assume that there is, since this is sliding along the ground. So a lot of times when you see something like this along the ground, not just something on the ground, but along the ground, that probably tells us there's going to be friction, because something is sliding. And again, friction is one of those forces that opposes motion. So if this object is moving to the right, or its velocity is to the right, and this is not a force I'm drawing, remember velocity is not a force, it's just how an object is moving basically, it's its speed and direction. So if this object has a velocity to the right, friction would act the opposite way. Now, in order for us to know how long we should draw this friction force, we need to know something about how this object is, again, either accelerating or not. So I'll draw 3 different situations very quickly down here below. So if we were told that this object were moving at, let's use a couple different colors here. If we were told that it was moving at constant velocity, that means that its speed is not changing and the direction of its motion are not changing either. Then this tells us that our forces must be balanced. So if something is moving at constant velocity, that tells us that the forces must be balanced. This is actually an application of Newton's first law, which I'll talk about in another video. But that means that not only do we have our gravity and normal force balancing each other out, but we would have this applied force and friction force also balancing each other out. And you'll notice I'm going to put 2 tick marks on these 2 forces. That's not to signal that these forces are stronger than normal force and gravity. I could put, again, 50 tick marks on friction and applied force. All that matters is that each of these forces have the same number of tick marks to say that these 2 forces must be balancing each other out right now. So that's the first case. If this were moving at constant velocity, this is what our diagram would look like. If, on the other hand, we were told that this is slowing down, then nothing would change about the gravity or the normal force. You'll notice those are going to be in every case. And we could draw our applied force like this. Still to the right because this person is exerting that rightwards force on purpose. It's a person doing it, so it's an applied force. But if this is slowing down and it's moving to the right, then the friction force is probably a little bit stronger, at least a little bit stronger than this applied force. And that's why it's slowing down, is because even though it's moving right, this leftward friction force is slowing it down. And then if this object were speeding up, let's do that in a different color, you can probably predict what that situation is going to look like. We're still going to have our gravity, Fg, our normal force, Fn. Since this object is not accelerating up or down, those are going to balance each other out. But now our applied force is going to be stronger than this friction force. So since not only is the object already moving to the right, or its velocity is to the right, but since it's also speeding up, this rightwards force must be causing it to continue to speed up, more so than this friction is causing it to slow down. That's why its velocity is still increasing there. Okay, so that was our first example. That'll be the longest one that we do today. But this is sort of the general case, and then these are our more specific cases if we knew more about the motion of this object and whether it were slowing down, speeding up, or moving with constant velocity, in which case those forces must be balanced. Let's look at a quicker example. So if a person is fallen and they're wearing a wingsuit, we watched a video of this in class, but if they're wearing a wingsuit to increase air resistance on them, which is a smart thing, that's like a parachute but on your clothing, let's draw a free body diagram on this person. So first thing, they definitely have the force of gravity acting on them, just as it acts on all of us, unless this person is skydiving from or in outer space, which would be pretty uninteresting and also dangerous. But now we're also told that they're wearing a wingsuit to increase air resistance acting on them. So it's helpful that we're told in this description that air resistance is acting. And air resistance we've talked about in class as being pretty similar to friction because it's also a force that opposes motion. So if a person is, or if an object or person is moving really fast to the right, air resistance acts to the left. If the person or object is flying up really fast, like a rocket taking off like we saw in class, then air resistance acts downwards on it. And the reason for that is that when something is moving, air molecules are literally hitting the front of that object. So whatever way that object is moving, if it's moving right, air pushes back to the left. If the object is going up, then air hits the top of it and pushes downwards on it. So since this person is falling, I'm going to label the direction of its velocity, right? So just like I did before, this is not a force, that's just a description of its motion. This person is moving downwards. But since we know that it's moving, or they are moving downwards, then the air resistance must act upwards on this person. Air molecules are coming up and bombarding the bottom of this person or the front of this person, assuming that they're falling face first, and pushing upwards on them. So there should be some kind of upwards air resistance force. Now, in order for us to figure out how long to draw each of these vectors, we would have to know again whether this person is speeding up, slowing down, or moving at constant velocity. If they were moving at constant velocity, these two forces would have to balance each other out. If this person were speeding up as they fall, gravity would be stronger than air resistance, kind of like how I've drawn it here. If we were told they were slowing down, then this upwards air resistance force would have to be stronger and drawn as a longer vector than this gravitational force. That's sort of a discussion from the last question of those three cases. There aren't any other forces acting on this person. They're not on a stable surface. They're not like on the ground. They're just falling through the air. So there's no normal force. There's no electrostatic force because we're not really being told about any charged objects interacting here. There's no springs. There's no strings necessarily. No one is purposefully applying any force to this person. So this is just about everything that we need for this free body diagram. Now, in this next example, we're going to look at a force that we have not yet talked about in this video. So now, a person is pulling a bucket of water up out of a well. So let's draw this free body diagram on the bucket of water. If I didn't label the object in the last video or the person in the last video, I should have. But if we have this bucket of water, we know gravity is acting on it for sure. That's a force that we can pretty much always start with. And if we remember how wells work, you need a rope to pull something up out of a well. So chances are, since we're using a rope in all likelihood, then we must have a tension force that's causing this bucket to come up. So anytime we have a rope, string, cord, or like in the Spider-Man example we watched in class, when Spider-Man was pulling on his webs, that was kind of like a tension force as well. We have that causing this bucket to go up. If this bucket were moving really quickly, maybe there would be air resistance, and in fact there is probably a small bit of air resistance, but it's going to be so small because this bucket probably isn't like flying up out of this well unless we're pulling it up really fast for some reason. If you wanted to be a stickler about it, you could draw a really small air resistance force downwards, and the reason that it would be downwards is because this velocity is upwards because this bucket is moving upwards, or we're pulling it upwards out of it. So that air resistance would be opposite of its velocity or opposite of this bucket's motion and be causing or be exerting a force downwards. So as the bucket is rising, air molecules are hitting the top and sort of pushing it downwards. I'm going to leave that out of here because usually if something is not moving really fast, like a person skydiving or something falling through the air, or like a bus, car, train, something with like a large surface area and moving pretty fast, we're usually going to ignore air resistance in these like slow cases. So this actually is our complete free body diagram. There's no normal force again because we're not on any stable surface, like this bucket is not resting on the ground or anything, or on any table or anything like that. No electrostatic forces, no charge, no springs, no applied force by a person, even though there's probably almost definitely a person on the other end of this tension force. It's probably more correct or more specific to call that a tension force. And this is our whole free body diagram. Again, if we wanted to draw the like sort of three cases, if this were speeding up, then our tension force would need to be stronger and drawn as a longer vector than gravity. because that sort of supports the velocity that this bucket has. If they were moving at constant velocity, or if this bucket were rising at constant velocity, these two forces would need to be balanced. And if this bucket were slowing down on its way up, our gravitational force would need to be stronger and drawn longer than this tension force. Those are sort of the three cases for this one. Okay. Now this one is a tricky one. This was on our homework, or pretty similar to our homework question. And now we have this football, and it's been thrown. That's an important thing that I'm saying. It has been thrown, not that it is still being thrown, and is now moving up and to the left towards its peak. So if I want to label the velocity of this, the velocity is kind of up and to the left. So we've thrown this ball, it's moving up and to the left towards its peak. And now let's draw the free body diagram on that. So the first thing I want to put on here is gravity, as always. It's going to get very old doing that, but it's so easy to forget. It's really important for us to remember that, even in situations where it maybe doesn't seem terribly relevant. It always is. Now, it's been thrown, so unless there's air resistance, and we'll talk about air resistance in a second, this would be the complete free body diagram for this football. Once a person lets go of that football, once it's no longer in contact with their hand, they are no longer exerting a force that probably once was upwards and to the left. That's why this football was put in motion upwards and to the left. But if they are no longer in contact with this football, then they're not applying a force anymore. There are no strings, there are no springs, there is no charged object that we're being told about. There's no other force really acting on here except for maybe air resistance. And take a second to think about what direction air resistance would be, knowing that the velocity is upwards and to the left, or that this is moving up and to the left. Remember, air resistance always opposes motion. So the opposite of up and to the left would be down and to the right. And in general, if this were a homework or quiz or test question or something, I would have to be a little more specific about whether or not you should include this little air resistance force, but it's at least a good exercise for us to think about what direction air resistance technically would act in, even if we're going to erase it or ignore it in certain situations. Okay, now here's a pretty long example. It's not going to take terribly long to do, but I'm going to draw a little more than I usually do. So right now we have a wall, that's here, the ground. We're going to have a spring attached to an object here. And on the other end of this object is a person with a rope. I'm not sure why they're doing this. They might be running a physics experiment. So we've got a person over here pulling this object to the right with a rope or a string or something. And then on the left side, this object is sort of being pulled with this spring because it's been stretched. So when we stretch a spring, they sort of pull back to compress to get back to their equilibrium length. Now, this example has a lot of different forces, and I included it because we haven't looked at very many spring force examples. But as always, we can start with the force of gravity. Now, the other thing that we know, since this object is on the ground, or on a tabletop, that's a stable surface, and so there's going to be a normal force acting on this object as well. And there's nothing telling us that there are other vertical forces acting on this object, so we are going to assume that those two forces are equal. They have to balance each other out. The other forces acting on this are a tension force pulling this object to the right, and the spring force pulling this object to the left. So I'll label both of those forces. Again, this is a tension force because a person has a rope and is pulling it that way, and this one is spring force because there's a spring there. Now, if this object were at rest, then we would know also that this tension force is equal to this spring force. That's kind of a special case of this object being at rest, or we could think about that as similar to an object moving at constant velocity. If something is at rest, its forces need to be balanced, just like for an object moving with constant velocity. And these are all of the examples that show sort of like the majority of those forces that at least we haven't seen before, where we've seen a lot of examples in Unit 1 of our electrostatic forces and gravity, but at least here now we've seen an example, at least one of each, for our gravity: normal force, applied force, friction, air resistance, tension, spring force. And remember to keep these sort of like key guiding principles in mind as we get into more complicated examples using really intricate details of Newton's third law, of Newton's first law, and then we'll talk more about how we quantitatively analyze these with Newton's second law.